Hello, and welcome to Controllerstech. In the previous video, I covered how to interface the SD card with STM32 using the SPI, peripheral, and DMA, demonstrating step-by-step how to set up SPI, configure DMA transfers, and communicate with the SD card directly from the microcontroller. The library supported all types of cards, standard capacity, SDHC, SDXC, and everything worked perfectly without compatibility issues. We achieved a write speed of around 194 kilobytes per second and a read speed of 200 kilobytes per second using DMA. Solid results for SPI communication. Today we will see how to use the SDIO peripheral to interface the SD card, offering a different, often faster method tailored for SD cards. Using SDIO will improve the read and write speeds drastically over SPI communication because SDIO allows wider data paths and higher clock rates. I have already covered a video in the past covering the SDIO peripheral, but a lot of viewers complained that the 4-bit mode was not working with it. So in today's video, we will fix that issue. Today we will use the SDIO in 4-bit mode, ensuring it initializes correctly and runs reliably. We will test the SDIO speed in 1-bit mode for bit mode and also with the DMA enabled to compare performance improvements step by step. I'm going to use the STM32F446 custom development board from UART Studio for this project. It's a solid board with full SDIO/SDMMC hardware support. This board has a slot for SD card at the back, which supports SDIO and SDMMC as well, meaning it's wired correctly for all modes we need. You can purchase this board in India from the Controllerstech store. The link is in the video description. Here is the schematic of the development board, so you can follow along with the hardware reference. You can see the SDIO pin connection at the bottom left corner of the schematic. This shows exactly which MCU pins wire to the slot. I will configure the pins in CubeMX according to this diagram to ensure electrical connections match. Let's start the Cube IDE and create a new project to get the code framework set up. As I mentioned, I am using an STM32F446RE microcontroller, which has built-in SDIO hardware. Let's give some name to the project and click Finish to generate the files. We will start with the clock configuration first, because the SDIO peripheral depends on proper system and peripheral clock settings. I am enabling the external crystal to provide the clock reference. This board has 8 MHz crystal on it, and we will run the system at maximum 180 MHz, which is the highest frequency for the MCU. Let's enable the serial wired debug interface so we can step through code during development and debugging. Now go to the connectivity section and enable the SDIO peripheral in 1-bit mode to start with a simpler configuration. Let's set it to 1-bit for now. We'll switch to 4-bit mode later in the video to compare timings. This way we will be able to test the transfer speeds in both modes and evaluate the performance difference. Let's remap the SDIO clock pin to PC12. That's exactly how it is wired in the schematic. In 1-bit mode, only one data pin is used, SDIO D0, so it simplifies initial testing. This pin is connected to PC8, and it is configured correctly by CubeMX based on the schematic. Other than this data 0 pin, there are also command and clock pins required for SDIO to operate. There is pin PA8, which is used to detect when the SD card is inserted, and we must set this pin as a GPIO input, so the MCU can read its state. Let's configure the peripheral parameters now to ensure correct behavior. The clock transition should be on the rising edge, which is the standard timing phase for SD card communication. SDIO clock divider bypass should be disabled so we can control clock frequency precisely. Disable the power saver feature for the SDIO clock to maintain stable, continuous operation. Enable the hardware flow control to help manage buffering and data flow under heavy loads. The final parameter is the clock divider factor. This determines the actual SDIO bus speed. This is the formula to calculate the SDIO clock frequency based on the system clock and divider value shown in CubeMX. Let's set the SDIO clock first to a safe test level. The maximum clock allowed here is 48 MHz. Let me configure the divider here to bring the SDIO clock within that range. 36 MHz is fine for initial testing. It's under 48 MHz and well above low speed mode. Now the SDIO peripheral clock is 36 MHz. If I use clock divider 0, the actual SDIO bus clock will be 18 MHz. The SDIO clock should be set within 187 kHz and 24 MHz during initialization phases, and we have the clock within this specified range. We will configure the DMA later for testing the speed improvements it provides over polling or interrupt methods. Now we will configure the FATFS Middleware to enable file system access on the SD card. Enable the SD card mode in FATFS settings inside CubeMX. Do not check the user-defined option since we will use the board support package, BSB, drivers provided by STM32 Cube. I am leaving all other options at their default values, except for enabling long file name usage. Let's enable the usage of long file names with a dynamic working buffer allocated on the heap. This allows longer, more flexible file names. The rest of the configuration remains at default values for simplicity. Now go to Advanced Settings in the FATFS section. Ensure the SDIO instance is set to SDIO. We're not using DMA yet, and the BSB code is set to generic. Now go to Platform Settings and configure the SD card detect pin to be PA8, matching the hardware design. We configured pin PA8 earlier for SD detect, so set that here so FATFS knows how to check card presence. That is all the configuration we need. Click Save to generate the project and HAL driver code. Let's copy the library files into the project from the downloaded package. You can get these files after downloading the project from the link in the description below this video. Place the files where I am showing, inside the SRC and Inc folders. The pre-generated code calls the MX SDIO SD init function during setup. Inside this function, it just configures the SDIO peripheral. It does not initialize the SD card itself. The actual SDIO initialization happens in the BSB driver SDC file. Here you can see the function HAL SD init is being called inside the BSB SD init routine. The parameters for this SD initialization are already configured in the main file, so no additional manual changes are needed. This BSB driver SDC file also contains other functions to drive the SD card, like read blocks and detect card presence. The SDIO.c file contains the driver glue code for FATFS, linking FATFS API to the BSB SD drivers. This file basically links the FATFS functions with the SD card BSB drivers, so f_read and others work correctly. Let's take a look at the library files we copied now. The SDfunctions.c file contains high-level functions to operate on the SD card. It includes functions like mount, unmount, write file, append file, read CSV, delete file, and so on. We will test most of these functions in today's tutorial to show how they work in real projects. Note that all these functions use the printf function to print logs to the console. So we need to enable UART to actually see these printouts in the console. I am using UART1 for this purpose, as it's easy to connect to serial via FT232. The pin PA9, UART_TX, is connected to the FT232's RX pin on the board. This way the data transmitted by UART will be received by the FT232, and hence it will be shown on your console window. Let's build the project again now that UART is enabled. Now define a custom write function, like _write, to route the printf data via UART1. Make sure to change the UART instance in that function if you're using a different UART port. Now we will test some file operations on the SD card. Include the SD_functions.h header in the main C file, so we can call those APIs. We will first mount the SD card, then list the files on the SD card, and finally unmount the card as a basic test. Let's build and flash the project to the board using ST-Link. Open the serial console and make sure the settings match the UART configuration in CubeMX, baud rate, bits, parity. Now insert the SD card into the slot and reset the board to start execution. You can see the logs have been printed on the console, confirming each step. The SD card is mounted successfully, indicating hardware and driver initialization work well. The card size is shown as 16 gigabytes in this example. The card type is detected as SDC, standard capacity, and the version is V1 of the SD spec. The mounting function terminates after printing the card class information. Then the list of files and folders present on the SD card is shown. I have already created some files and folders for test purposes, and they're being shown here in the output. At last, the card was unmounted successfully, completing the test cycle. The mounting and unmounting works fine. Now we will read a file from this SD card. I will read file 5.txt, which is inside folder F1, F2, and that folder itself is inside another folder F1. Let's define a buffer to store 100 bytes of data and a variable to store the number of bytes read from the file. Now we will first mount the SD card again. Then we will read data from file 5.txt and store it in the buffer we just defined. The buffer is 100 bytes in size, and the number of bytes read will be stored in the variable BR. Now print the buffer contents to the console and then unmount the SD card again. Let's build and flash the project to the board for this test. You can see on the console that after mounting, 30 bytes are read from the file 5.txt file. Then it printed the data from the file correctly. And finally, the SD card is unmounted, ending the read test. Let's include the standard I/O header file, SDIO.h, so the printf calls work properly. Now we will write data to a file on the SD card. First mount the SD card, then call the function SDWriteFile to write data to file 8.txt. If this file is not present on the SD card already, the function will first create it and then write the data to it. Then we will read this file back and store its data in the buffer we created earlier. After reading it, print the buffer to the console and unmount the card. Let's build and test this project again to verify the write process. As you can see in the console, after mounting the card, 52 bytes were written to file 8.txt. The file is read back, and it is then printed on the console to confirm the content. So the write operation works just fine. It's reliable and repeatable. Let's test appending data to an existing file next. Call the function SD append file to append additional data to file 8.txt. We will again read the file back and print the updated data on the console. Let's build and flash the project to the board for this test. You'll see here that 31 bytes are appended to file 8.txt. The file was originally 52 bytes in size, and now, with appended data, is 83 bytes total. This is the data read from the file, containing both the original and the appended content. So appending data to the file works fine as well. We've verified that functionality. Now we will read a CSV file from the SD card. The SD_functions.c file contains a separate function called SDReadCSV to parse CSV data. Call the function SDReadCSV to read the CSV file. I have already stored a CSV file named file4.csv inside the F1, F2 folder on the SD card. Provide the correct path to this file when calling the function. There are some additional parameters to this function as well. You need to pass a CSV record structure pointer, a max records limit, and get back record count. Let's understand these parameters first before calling it. CSV records is a structure that contains two fields to store data from two columns in each row. If your CSV file has more or fewer columns, you can modify this structure accordingly. The variable max records defines the maximum number of rows the function will read from the file. And record count stores how many rows were actually read during the operation. Let's define these parameters in the main function first before using the function. The CSV file I copied on the SD card contains 16 rows, so I am defining max records equals 20. Now define a CSV records array to store the data read from the file, and a variable to hold the number of rows read. Let's pass these variables to the SDReadCSV function for processing. This function itself prints the file's data to the console, so we do not need to manually printf each entry. Let's go ahead and debug the project now to see how the data is stored inside the CSV record structure. Let me put a breakpoint inside the while loop of the CSV reader function and run the debugger. The breakpoint hits, but there was no data on the console initially. The log output shows that it failed to open the file. Turns out I named it incorrectly. Alright, let's fix that file name and launch the debugger again. We have hit the breakpoint again, and this time you can see the record count is 16, meaning the function has read all 16 rows. Here you can see the data from the CSV file printed in the console output. There are 16 rows in total, indexed from 0 to 15. The lines 01, 02, 03 correspond to row numbers and columns, while 1C, 2O, 3N are actual cell data. Here is how the data is stored inside the CSV file on the card. We have a total of 16 rows with 2 columns each, and this is exactly what is printed to the console. Let's see how the data is stored inside the CSV record structure. Note that I am viewing the data in the Variables tab of the debugger, not the live expressions. These variables are defined locally, so they appear automatically when the debugger pauses in that scope. The Field 1 member contains data from the first column, and Field 2 contains data from the second column. The data is stored in character format, which makes it suitable for display or transmission. So reading the CSV file works correctly and cleanly. We have now tested several of the functions available in the SD_functions.c file, and you can test the others as well for more functionality. Let's test the transfer speed in 1-bit mode now, and later we will do the same for 4-bit mode with and without DMA. The SD_benchmark. The C file can be used to benchmark SD card performance. You can adjust the file size used in the test. I am configuring it to 1 megabyte for accurate results. So we will write a 1 megabyte binary file to the card and then read it back to measure transfer speed. The write and read speeds will be calculated based on this round-trip transfer. Include the SD_benchmark.h header file inside main.c to access the function. Now call the function SD_benchmark inside the main function. The mounting and unmounting of the SD card will be handled by the benchmark function itself, so we don't need separate calls. Let's build and flash the project to the board for benchmarking. As you can see on the console, we are able to achieve around 590 kilobytes per second write speed and 1.4 megabytes per second read speed during the test. Let me test it a few more times to ensure consistency in results. We can conclude that the write speed is around 600 kilobytes per second and the read speed is around 1.4 megabytes per second in 1-bit SDIO mode. This is way higher than what we previously achieved using the SPI interface. We will now enable the 4-bit mode for the SDIO peripheral and test the speeds again to see the improvement. Open CubeMX via CubeID, go to the SDIO section, and change the mode to 4-bit wide bus. This mode uses 4 data lines, so we need to reassign pins according to the hardware schematic. Let me change the pins now. As per the schematic, PC8, PC9, PC10, and PC11 are the 4 data pins. PC12 is the clock, and PD2 is the command line. We do not need to modify other parameter configuration. Click Save to regenerate the project again. Assume that we'll test the SD card with this default generated setup. Let's build and flash the board, then test again. As you can see on the console, the mount function fails immediately in 4-bit mode by default. This is because the SD card isn't able to initialize directly in 4-bit mode. It requires 1-bit initialization first. Let's take a look at the MX SDIO SD init function in code. Here, the SDIO peripheral is configured for a 4-bit wide bus before any card initialization happens, causing the failure. As I already mentioned, the actual initialization of the SD card takes place in the BSB driver SDC file. And if you note inside that file, the driver enables wide bus operation only after the card has been initialized in 1-bit mode. So our mounting fails at the SD initialization function itself, because the SD card won't initialize in 4-bit mode directly. Instead, we need to first initialize it in 1-bit wide mode, and then let the driver configure the bus to 4-bit afterward. If you set it to 1-bit mode here in CubeMX, it will get overwritten when the project is regenerated. It is better to enforce it in the user section of the MX SDIO SD init function so CubeMX doesn't overwrite it. This is the only modification we need to make the 4-bit mode work reliably. Let's build and flash the project again to test this fix. You can see the card has initialized successfully this time, and we get higher read and write speeds. Let me test it a few more times to confirm stability. We can say that in 4-bit mode, we are able to achieve around 700 kilobytes per second write speed and 2 megabytes per second read speed, significantly improved compared to 1-bit mode. To make 4-bit mode work, you must initialize in 1-bit mode first, then let the function configure wide bus operation be called afterward. Now for the final test. We will also add DMA to the 4-bit mode configuration. Open CubeMX again. Go to the SDIO section and then the DMA settings. You can enable DMA for specific transmit or receive operations, or simply select SDIO to enable both channels automatically. The mode should be set to peripheral flow control, FIFO threshold set to full, data width to word, and burst size to 4 for optimal speed. Now go to the MVC tab and make sure to enable the SDIO global interrupt. This is necessary, or else SDIO DMA writes won't work properly. Now go back to the FATFS section, open the Advanced Settings tab, and enable the DMA template for FATFS. That is all we need to enable for the DMA setup. Click Save to regenerate the project once more. Even after regenerating, the modified SDIO initialization remains intact because we placed it in the user section. That is why we define that change manually, so it won't be lost during code regeneration. We do not need to modify the test files or benchmark code. Let's build and run the project again. You can see the write and read speeds have noticeably increased with the use of DMA now. Let me test it again to confirm the results. We can say that we are able to achieve around 740 kilobytes per second write speed and around 2.5 megabytes per second read speed with DMA enabled in 4-bit mode. So in summary, we saw how to interface the SD card using SDIO in 1-bit mode, then in 4-bit mode, and finally in 4-bit mode with DMA for best performance. The read and write speed using SDIO is way higher than what we achieved with SPI, and improves further with 4-bit mode and DMA enabled. You can also test the rest of the convenient functions present in SD_functions.c, like file deletion, CSV parsing, and directory listing. You can download the full project, including all source files, from the link in the description below this video. The library files are located inside the src and inc folders of the project directory. We will continue this series in the next video, where we will use the STMMC peripheral to interface with the SD card and further improve performance. That is it for this video. Leave comments below if you have any doubts or suggestions. Thanks for watching, keep learning, and have a nice day ahead.